Hello, my name is Margaret Bridgers, and this is Lab 3, Magnetic Field of a Bar Magnet. In this lab, there are some skills that we are improving. First, we are working with dipoles and GlowScript in Python, and we're also working with magnetic fields and working with dipoles. The goal of this lab is to produce a visual representation of a magnetic field and this is used to view a dipole and to calculate the mu of the dipole experimentally. We do this by treating the bar magnet as a dipole. We then also use this to find mu of the bar magnet by measuring the strength of the magnetic field at different distances. There was a bit of setup that needed to be done to start this experiment. First, we had to calibrate the x component of the magnetometer to 0 to confirm the direction of north. Next, we needed to find the location of the magnetometer on the phone application. Then, we needed to lay out the magnet horizontally at the end of the ruler with the magnet on the front edge of the ruler. Then, we needed to figure out the location of R where the magnetometer picks up the x component of 1000 μt. Then we needed to record the components at distances R20, R70, R120, R170, and R220. Then we needed to calculate mu of the bar magnet dipole given the conducted data findings. To the right are the experiment recordings of the magnetic fields at the specific distances. Here we can see that ln of R and ln of B were used to find the ln of K value, which is the y-intercept presented in the graph. We know that theoretical end value should be close to -3 when it comes to the slope, so I am slightly off, but that could be due to error when conducting the data and using the application to calculate the magnetic fields. Next, for the code, we wanted to visualize the magnetic field at different distances or points of the bar magnet. We first defined the mu value that was found using the experimented data from the previous slide, and then we defined the electric field of the dipole using mu naught and R vector. We then created a representation of the arrows at the different distances from the bar magnet. First, we had to define the on-axis and perpendicular arrows of the mu vector of the dipole magnet. We wanted to create a 45-degree angle from the mu of the dipole so that we could compare this angle from what we measured or calculated to what the formula says that it should be. Here's a picture from the book. This is just a representation of what the magnetic field of the bar magnet should look like, and I feel like this will help us better understand the outcome of our code. Here's what the code produces. We can see that the arrows on the axis are straight. We also know that the magnetic field loops around and then comes back up. This is an explanation for why the perpendicular arrows are going in the opposite direction. The green arrow is the one that is at 45 degrees. Here you can see the results, and we can see that we are somewhat in close vicinity from our calculated observation to for the B magnitude of 45 degrees. So, what ifs? What would happen if we had not had oriented our magnetometer? Well, the reason that we oriented it was so that we could get rid of the Earth's influence on the magnetic field. So, if we had not oriented it, we would have to factor in the Earth's magnetic field in our calculations and our findings. What if we redid the experiment by sticking 2 magnets end to end and redoing the experiment? Well, the magnetic field would get larger and stronger. This does not mean that it would have gotten stronger and larger by a factor of 2, it just means that the strength and the size would both increase. Thank you so much for listening.